Okay, let's start this class. Do you remember what did we talk about last class, in last class? Do you remember? Yeah. Step function, impulse function, and lastly, we talk about what? CT-DT systems. Do you remember that? Yeah, we talk about what is signals, what is systems, and what is CT systems, what is DT system. Today we will talk about the basic system properties. Yeah, for the CT system, DT system, there are some like basic properties for those systems. Okay, let's review today's goal. Firstly, we will review how to mathematically characterize CT and DT systems. And then we will try to define four basic properties of a system: memory or memoryless, invertibility, and correlated, and stability. Yeah, and actually we have two, and we will talk about in next class. Yeah, and after that, and we will try to decide the four properties for a given system. Yeah, because every system will have those properties. Yeah, and okay, let's talk. Let's try to review the how to like mathematically characterize the systems. Okay, we know like the CT-DT systems allow us to analyze the process and manipulate the signals according to our needs. Am I right? Like usually the CT-DT system is just like I have an input, signal input, and then I analyze, manipulate these these signals, and then I output the other signals like that. Yeah. So. Yeah, this is system, and this is just like the diagram for the CT system. Like for the CT system, and the input should be the CT signals, and the output is also the other CT signals. And the DT is a similar thing, but the input is just like the discrete signal, and the output is discrete, the other discrete output. Yeah, and this is just the CT systems from the input to the output. And this is the DT system from the input to output. Yeah, that makes sense to you? Yeah, okay. Then let's talk about the difference between the CT system and the DT system. Do you remember like we know all the first order linear invariant system can be represented in a specific form. Do you remember what form? Do you remember? Yeah, we talked about in last class. Yeah, this one. The first order differential equation. Like we know all the first order discrete systems can be represented like this. And for the DT, the first order difference equation. Yeah, this is like a differential equation. This is difference equation. Like we have this. Yeah, you can see it's very similar. Yeah, one is differential, the other is difference, and we also have the conclusion. All CT-DT systems that can be written as a constant coefficient differential or difference equations, like are linear time invariant systems, which means all CT-DT LTI systems can be written as those form. Does it make sense to you? Yeah, all the CT-DT linear time invariant systems can be written as this form. Yeah, this is very important because we mainly focus on the first order CT-DT time linear invariant system, and we will mainly focus on LIT system in chapter 2. Okay, any questions so far? Okay, let's talk about some basic properties for the linear system for the CT-DT system. The first one is memoryless. Yeah, which means systems memoryless, which means systems without memory. And what is memoryless? And what is memory? Yeah, in a memoryless system, the output yt or yn at a given time depends only on the input xt or xn at the same time. Yeah, which means after we reading this one, like do you feel confused? Like the output, like for the CT-DT system output, only depends on the input, the same time input. It will not depend on the previous signal. Also, it will not depend on the future signal. That makes sense to you? It only depends on the same time input signal. Yeah. For example, memoryless DT systems. You can see here. This is input. This is like output. This is input. I just want to actually the YT is not a system. The whole equation is a system. All right. The xn is just the input signal. The yn is just the output signal. Yeah, the whole thing represent a system. That makes sense to you? Yeah, you can see the output only depends on the at same time input. That makes sense to you? Yeah, the n only depends n. It will not depend n plus 1. It will not depend n minus 1. It only depends on n at the same time. That makes sense to you? Yeah, so this system is a memoryless system. Okay, let's see the other example. A resistor is a memoryless CT system. Yeah, we know this is a current, this is a voltage, and this is current will change as a time passing. Yeah, and also the voltage will change as a current change. Right? This is a memoryless system, which means your right now current voltage just depends on the right now current. Yeah, it doesn't make sense. Does it make sense? Yeah, when you do the lab, yeah, the output voltage only depends on the that time in a current. That makes sense to you? Yeah. So this is memoryless system. And how about this one? Yeah, give me a is it memoryless or non-memoryless? Like a memory. Yeah, actually this is a tricky one. Yeah, let me see. This is the current at the same time input time, right? Yeah, but here there is a t. T is the same time, am I right? That time. T plus 3. If the time is fixed, t plus 3 is fixed, am I right? Cosine t plus 3 is also fixed because this is a value. That makes sense to you? Yeah, it will not be. Actually, just remember, when you talk about the memoryless or the non memory, you just find the relationship between the input and the output. Yeah, other things you just ignore that. Yeah, because you can see this part when the t is fixed, the value for this part will be fixed. Does it make sense to you? Yeah. So this one is also memoryless. Yeah. Does it make sense to you? Okay, let's see the other question, the other example. Okay, then let's talk about the memory, systems with memory, which means for example, accumulator or summer. You can see this one. The output not only depends on at same time input, it depends on the previous input. Does it make sense to you? Yeah. So which means this one is a memory system. And then a delay system, yeah, this one, yeah, which means that the output not only depends on the same time input, it's just depends on the delay, the previous time input. That makes sense to you? Yeah. So we call it is a system with memory. Yeah, you can say when ND is a fixed positive integer, which means it is a previous time. Am I right? Yeah, if it is a negative, which means it is a future time. Yeah, I'm right. Yeah, so it will it will depend on the previous or the future. It will not just depend on the like the same time. Yeah. Okay. Also, capacitor. We know like a capacitor is just like the charge. It has a charge process. Am I right? So it will like try to like integral the current, like then give you a C, like multiple 1/C. Then you have the voltage like that. Am I right? Yeah. So it is a system with memory, because you can see it is a process. It not depends on, it not like the resistor circuit, only the resistor circuit. It depends on the previous tap current. That makes sense to you? Yeah. So this is like a system with memory. Yeah. The Y is voltage, X is current. Okay. Let's then any question for the memoryless and memory? Yeah. Memoryless. What does that mean? Yeah, at the same time, the memoryless, the memory, which means it depends on the previous. Am I right? Yeah. Okay, let's talk about the other property, invertibility. Yeah, which means this system can be inversed. Yeah, if a system is invertible, then an inverse system exists that will cascaded with the original system yields an output equal to the input to the first system. Yeah, let's try to understand what does this mean. Which means you have a system, and this system, after the system, you have an output, right? Then after an inverse system, you can have the original input, which means this system is inverse. Yeah, we call it inverse system. That means, does this make sense to you? Okay, and like why do we need the inverse systems? Can you think about some real world applications? Why? Yeah, actually, the inverse system is very important. Is very common and very important. Yeah.
Back to like say.
Yeah. That's true. That's true. Can you give me an example? Yeah, actually, let me give you a very easy example. Like when you use your phone to take a picture, am I right? Like which means your phone is a system. We know that. And the real world image scene is the input, and then you got the camera digital image. And but when you take a picture, your phone maybe will bring some noise. Am I right? Yeah, and then you want to. Then you found out your image is very blurred, or maybe it's very noise. So the real world scene, you want to get the real world scene. You don't want this one. Am I right? So you need to have an inverse system to get the real world scene. Then yeah, this is a very like a common like example. Yeah, you know, like when something when signals it goes through some systems, it might be changed. Yeah, it might be changed, it distorted. Yeah, then you want to get the original one. So that's like why usually we need the inverse system. Yeah, you can see sometimes after a distorting system, you get some output, but it's so messed up, and then go through the compensating system. Then you got like an original one. But you remember, usually after the compensating system, we get an input, get a signal. But this signal is very similar to the original one, but it's usually it will not the exactly same. That makes sense to you? Yeah. Okay. Any questions so far? Yeah. Okay. And then let's talk about this one. You can see, like this is the system. Like we go through this system, we get a YT, right? This is input, this is output, and this is the inverse system. And after the inverse system, we can get XT. Then try to tell me, for the first inverse system, what is this inverse system? What is it exactly? You know? which means the first input YT, am I right? And after like the inverse system, and then your output should be XT, am I right? So which means your YT will equal half XT. For example, this is 1, and this is 1 ST. Actually, this X1 T is exactly this part. That makes sense to you? And then you will go equal this one. That makes sense to you? So this is just the inverse system. That makes sense to you? Yeah. So and also this one. For example, this is like input, and then you got this one, and this is one. And how can you get after the inverse system? How can you get X? Yeah, you also can have try to. This is YN. Yeah. Let me see. Yeah, and this is a Y equal X. Okay, and then Y2 try to get opposite this one, and then we can get X. Right? Which means what you can do? What you can do? What you can do? Yeah, actually you can see, which means you just get the value when like n, right? N one atom. That makes sense to you? How can you do that? Actually, it's very easy. Here you have this one. Then you want to get the xn. How can you do that? Yeah, this is just like what's this? This is x that from negative infinity plus x negative infinity plus 1 plus blah 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 until plus am I right? This is just this part, am I right? So for now, I just want this item. What can I do? Just remove the previous one, am I right? How can you remove that one? Yeah. What 0?
A.
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 Yeah, actually it's easy. How can you remove this part? How can you represent this part? I think this one is easier, right? This question. Yeah, you represent this whole part as this form. Now how can you represent this one? Yeah, here is n. And then if I want to represent this part, how can I do it? -1. That makes sense to you? Yeah, if you just modify this to -1, it's just like the previous part. That makes sense to you? Yeah, which means if you want to get this one, you just minus k n-1 xk. That makes sense to you? Yeah, which means this is just this system. Yeah, so like I know that makes sense to you? Yeah, those two. Yeah, actually it is yn plus, yeah, this is just a yn. Right, this is just yn -1. That makes sense to you? Yeah, so actually those two example is not that difficult. Yeah. So yeah, we know this is just what I just get. Yeah, and these two examples are not that difficult to get, but usually in practice, it's more convenient to use the transfer function to find the inverse system for a given like system. The transfer function we will talk about in the following class, because the transfer function is the other area we need to talk about. Okay. Yeah, actually, I just want to tell you the invertibility is a very important property for a system. Yeah, that makes sense to you? Okay. Any question about the invertibility? No? Okay, let's talk about the third one. Correlated. Like, which means we will decide if this system is causal or non-causal. Yeah. A system is causal if its output at any time depends only on values of its input at the present time or in the past. It is also non-anticipative, which means the output only depends on the present time or the past time. It will not depend on the future time. Yeah, that if it is only depend on the present time or the past time, we see it is causal. Otherwise, it was non-causal. Okay, let's talk let's view some examples. Yeah, for example, this one. Why this is non-causal? Do you know why? Why? Yeah, I have already given you this is non-causal. Why this is non-causal? Huh? Memoryless? Yeah, just memoryless. Okay, just review the definition. The causal system only depends on the value of its input at the present time or in the past. Am I right? But here, did you notice that this is the present time? Am I right? What's this time? What? This is for example, when my time is 1 second here, 6 o'clock, am I right? Here at the present time is 6 o'clock. What's the time for this one? 6:01, am I right? So what's the time for this one? It's a past time or the future time? Yeah, it is a future time. So that's the reason why it is non-causal, because it not only depends on the present time or the past time, it depends on the future time. Does it make sense to you? Yeah. Okay, let's talk about this one. Why this is non-causal? The same reason, am I right? Because t is like a present time, and +1, which means it is a future time. Am I right? Yeah. Okay. How about the memoryless time? Memoryless system. Yeah, actually, I think Matthew is right. You just talk about the memoryless system. Is the memoryless system causal or non-causal? Yeah, it will be causal. Why? Yeah, it only depends on the present time. Am I right? So the memory time, it must be like a causal. Yeah, but a causal system will not be that like a possibility like has some possibility to be like memoryless or non-memoryless. Does it make sense to you? Yeah. Okay. How about a moving average system? This one. Yeah. How about this one? It is a causal or non-causal? Yeah. What for the definition? If this system depends on the past time, am I right? Depends on the present time or the past time, and then it will be causal, am I right? So if k greater than 0, am I right? Which means the n should add a positive integer, am I right? It will be future time, am I right? So it will be non-causal. But if k like greater than 0, which means n minus integer, am I right? That makes sense to you? Yeah. If k smaller than 0, which means this part will become, for example, k equal -2, and this part will become x plus 2, am I right? Is this the future time or? Yeah, future time, which means it is non-causal, am I right? Yeah, if k equal 2, and then that it will become n like -2, am I right? So it is past time, am I right? So it is correct. So like for answering this question, you need to think about that. Like it will depend, am I right? Yeah. Yeah, when M2 greater than M1 greater than 0, which means P greater than 0, right? Greater or equal than 0. And then this, which means it will be correct. Otherwise, if M1 smaller than 0, which means P can be a negative value, right? So it will be non-correct. That makes sense to you?
Yeah.
Yeah. Okay, let's continue. Let's check more example. How about this one? Yeah, actually this one is a little tricky. How about this one? Yeah, actually for this system, you can try to some examples, am I right? Yeah, if n equal 1, like then x you need to figure out x -4, am I right? Am I right? Am I right? Yeah. N equal 1, x should -4, am I right? Yeah, then if n equal -1, what is x here? -2, am I right? Yeah. But if n equal like a -5. Is -5? Yeah, if it is n equal -5, x what? +2. So it is a feature of past. If n equal -5, which means your time is your time, present time is here, am I right? While n is here, but your x is here. Your input is this time. So which means your output depends on this time the input, the future time input, am I right? So is it correct or not correct? Yeah, that's true. Because it not only depends on the past, sometimes it will depend on the future. That makes sense to you? Yeah. How about this one? Are you sure? Yeah, actually, yeah, you just think about that. Yeah, it is non-correct. You can see here, if your t greater than 0, yeah, half t, absolutely it will be passed, I'm right? But if your t smaller than 0, and then your half t will be the future time. That makes sense to you? Yeah, so it will be non-correct. Yeah. How about this one? Yeah, because it just depends on the present time. Yeah, you just remember if your t is fixed, this value is just fixed. Am I right? Yeah.
Actually, it's awesome if you put in negative time, it doesn't make the number any smaller.
You can try, but sometimes you need to think about like opposite example. Sometimes you cannot find all the example. Am I right? Yeah. So you just need to find an example to tell if it is non-correct. Yeah. That makes sense to you? Yeah. Okay. And how about this one? Yeah. Yeah, because it only depends on the previous time. But this one is just the way your t is fixed. This is a fixed value. Am I right? Yeah. Okay. How about this one? How about this one? Yeah. Yeah. Because it only depends on the previous time.
Plus,
You can you know, like you mean, oh, here I plus I minus one, right?
I was thinking like the n plus one on top.
Oh, but this is not the system I give you. I give you this system. Yeah, and I want to tell you the difference here. You can see this is here we can try to because M2 M1 it have some different situation. I'm right, but you can see I will never change if here is n because n is just like the time variable I give you. Yeah, but here it's just the other variable. You can change it. You can decide it you can judge in different situation. Yeah, but here you cannot because this is the system I give you. That makes sense to you? Okay. Yeah, so this is Coral. Yeah, how about this one? I think this one is obvious. Yeah, this is just I give you the system. This is here is a plus 5. Huh? Carol, not Carol? Yeah. If you try to find what is the present time, you just see here. Here is only the present time. Yeah, so non-Coral. Are you sure? Yeah, what's a present time? N, I'm right? Yeah, it will like add the k from like negative infinity to the n plus 1, n plus 5. So what is it? Yeah, it is non-Coral because it will depends on the previous future time. I'm right? Does that make sense to you? Yeah, any question? Okay, yeah. Which means the king is examining the relationship between input and output. Yeah, just try to examine the input output. Here it's just like ignore it. Here it's just because it's just like yeah, that makes sense to you. Yeah, okay. Let's talk about the other property, stability. Yeah, and stability, which means if we want to tell whether system is stable or non-stable system, a stable system is one in which like any finite, we also can see it bounded input, which means your input has some range value, am I right? It will smaller than infinite. These two finite output, yeah, bounded output. Or we can call it BIBO, which means bounded input, bounded output. Yeah, if your system has a bounded input and a bounded output, which means your system is stable. Otherwise, your system is non-stable. Yeah. Okay, I think the definition is clear. I'm right. So let's talk about some examples. How about this one? This system. Yeah. What is this system? Yeah. The input is bounded. Am I right? Yeah, how about the output? What's the name for this is RC circuit, am I right? I think you do many labs for this one. So the input definitely will be it's bounded, am I right? If you do the lab. How about the output? It is your output is bounded or non-bounded? Huh? It is changeable. Changeable doesn't mean unbounded. Bounded, which means bounded output, which means it is smaller than infinite. It will be bounded. Yeah. Changeable and the bounded is a different thing. So output is what? Bounded. Am I right? So this system is BIBO system. Yeah. How about this one? Yeah, the force is bounded, am I right? You cannot give infinite force, am I right? And the output, the velocity, yeah, in the real world, it must be infinite, am I right? So it is a BIBO system, am I right? Yeah, so your force cannot be infinite, and your velocity cannot be infinite. That makes sense to you? Yeah, so those two are like a stable system. Yeah, okay. Which means if your system is a LIT system, yeah, the first order IRT system, your system must be stable. Yeah, it will not be an unstable system. Yeah, that makes sense to you. Yeah, which means when you do some, when you build some system, when you try to do some lab for the robotic, you better to try to construct your system as a stable system. Because stable system, which means your input will result, your bounded input will result like a bounded output. Yeah, and your system can be improved, can be like a measurement. Am I right? Yeah. Okay. Yeah, they are stable. Okay, let's talk about this one. How about this one? It is stable. Yeah, what? Yeah, it is unstable. Yeah, you're right. Yeah, actually, you're right. Yeah, but what? Yeah, first let's talk about like we know for this system like when we talk about system we consume like all the input is bounded. Yeah, when we talk about those examples, we just consuming like all the input is bounded. Let's check like if the output is bounded or not bounded. Yeah, for this one. Yeah, it's unbounded. Because you can see here, we need to add infinite atom x input, am I right? Yeah, infinite input, which means it might have infinite value, am I right? So this one is unstable. Yeah. Well, how about this one? Yeah, we know we know like the input is bounded. The output is what? Are you sure? Yeah, you can see. I just talk about when we talk about this system, we always consider the input is bounded. This is the condition I give you. This is bounded, which means x 3t plus 2. If it is bounded, if xt is bounded, if this one is bounded, it is right. So this is just a yt. If yt bounded, am I right? Yeah, because this one is bounded. This is just like a plus 2 and like a add 2 plus 3. It's just like a some t, am I right? Some t, yeah, am I right? So this one is stable. That makes sense to you? Yeah. Okay. Let's talk about this one. How about this one? Like we know. Just remember, I give you the condition. The xn is bounded, which means the xn plus 1, it is bounded or not bounded. It's bounded, am I right? So x minus x it is bounded or not bounded. One bounded value minus the other bounded value. It will bounded. Yeah. So this is stable. Yeah, and then let's talk about this one. How about this one? Yeah. Okay. Yeah, let's talk about this one. Firstly, we know the xn is bounded, right? Here, xn is bounded. Yeah, you can see this one and this one is similar, right? But the difference is this one has what? Yeah, here the key will added from infinite, but here it will from n1 to n2, which means the output should be some bounded signals added together. Am I right? Yeah. So if it is bounded or not bounded? Bounded, am I right? Yeah, because you just bounded. Yeah, it is stable. Okay, let's try to see one more example. This one. Yeah, this one. E xt. Here I just give you the xt. It's just a bounded signals, and then let's talk about the output is bounded or not bounded. Here, this is like the exponential signals when you draw it. This is f x or the ex. This is e negative x. If you like draw it, am I right? Yeah, which means we know like the input is bounded, am right? So which means we can write the input signal like this is smaller than the absolute value smaller than b. B can be some value, am right? Yeah, we can write this like this, and then which means xt smaller than negative b and greater than negative b, am right? The smaller than negative b greater than smaller than negative greater than negative b smaller than b. I'm right, sorry. And then which means we can have which means the like x here, this is x, can be this range, this range, this range, and right? B can be any value, right? So but your output you can see is bounded or non-bounded. Yeah, it is bounded. Yeah, because you can see you just like try to get a range for this image, for this figure, am right? Yeah, so yeah, y t is just in this range. That makes sense to you. So this is which means this is bounded output. So this system is also stable system. That makes sense to you? Yeah, any questions? Okay, let's try to. Yeah, if you want to tell a system is stable or not stable, there is a very useful trick. If we suspect that a system is unstable, then we can verify this by looking for a specific bounded input that leads to an unbounded output. Yeah. Here, this one. We can like we can just try to find a specific bounded input. For example, we can let xt equal 1. Am I right? Yeah, we know like the xt is a bounded system. Bounded signal. Am I right? So we just consume it is 1. It can be 2. It can be 3. But the result will be changed. Am I right? Yeah. So then your yt equals. If xt equal 1, and then your output should be like this, am I right? So is this bounded or not bounded? What's t? Time, am I right? Time is from negative infinity to the positive infinity, which means your output is unbounded. Yeah, that makes sense to you? Yeah. So which means this system is like unstable, and you can see here. Let us to make the xn equal 1, right? Which means this one should equal like n squared, right? And then it is if it is infinite or finite, then greater equal 0. So this is infinite or finite. Huh? Unbounded, yeah. Yeah, because you can see the n will go to infinity, right? Yeah, so this one is it's unstable system. And you can see, let's try to use the same thing here. Here, if you let the xn equal 1, look at me. Yeah, if we let xn equal 1, which means we just replace x key 1, right? And then which means the infinite 1 add together, what's the value? Infinite, am I right? Yeah, and how about this? We let xt equal 1, which means x3t plus 2 will equal 1, am I right? Which means yt equal 1. It is bounded, am I right? Yeah, so you can use that method we just talked about too. Yeah, here is 1. If you let this is 1, this is also 1. 1 minus 1, it is 0, am I right? Yeah, similar with this, it is 1. And then you just use n minus n2 minus n1 minus plus 1 like number 1 add together, so it will be bounded. That makes sense to you? Yeah. So this is just like a useful trick. You can use these things to judge if it is stable or non-stable. Okay. Yeah. This is the system. CT system, like mathematical characterized, and then 4 different like properties. Let's do a summary. What are those four properties? Do you remember? The first one is memory, memoryless. The second one is yeah, invertibility. I'm right. Invert system or non-invert system. Okay, the third one is causal, non-causal. Let's try to review like memoryless. What is memoryless? Yeah, depends present, only depends on present. I'm right. Yeah, and otherwise it will non-memoryless. And the inverse system, which means can be through the inverse, it can transfer the output to the original input. I'm right. And the like causal, what is causal? Only depends on yeah, only depends on the present part and the present time and the past time. Yeah, otherwise it will be like if it depends on future time, it will non-causal. Yeah. Then the last one is stable. Yeah. How like what is stable? Yeah. Yeah, bounded input result in bounded output. Yeah, otherwise, if it is a bounded input, non-bounded output, it will not be stable. If it is non-bounded input, non-bounded output, it definitely like not stable. That makes sense to you? Yeah, we will talk about the other two properties next class, and then we will finish the chapter 1, and we will review the midterm 1 on next Monday, and have the midterm 1 on next Wednesday. That makes sense to you? Okay, any questions so far? Okay, that's great. Yeah, just remember to finish the homework as soon as possible. Yeah, otherwise you will feel it's